This lecture deals with linear prediction. I think these two quotations sums up the problem pretty well. It is not hard to predict the future, the problem is to do it well. A linear prediction is formed as a weighted sum of earlier observation. You basically combine n earlier measurements and form your prediction using those. For a Gaussian process, this is an optimal predictor, meaning that you cannot form a better predictor of the future in any other way. Of course, the problem is then how should I select the weights of these earlier measurements to make this a good prediction? The way to do that is that you exploit the orthogonality principle that we discussed before. You are basically saying that I want the prediction error to be orthogonal to the data I've observed. The way you do that is you take the future, the true future, and you predict it onto the range space spanned by the observed measurements that you have. The resulting prediction thus lies in the range space of the earlier observation. It only consists of a combination of earlier observation, and therefore you can write it as a sum of earlier observations like this. As you know from our earlier discussion, the error between the prediction and the future should be orthogonal. Expressed differently, I can form a cost function, which is the variance of the prediction error like this. That is the same thing as the covariance between the two prediction errors, which if I write it out will be the covariance between the prediction error and the future measurements, as well as the prediction error and the predicted future values. However, as we know from the principle of orthogonality, these two vectors will be orthogonal to each other, so this will be 0, leading to this expression. Thus, I can form the weights by minimizing this cost function. Let's look at an example. This is an MA1 process. Assume that you have observed y1 and y2, and you want to form an optimal linear prediction of y3. You can do that by noting that the prediction error between these two should be orthogonal to the observed data for the 2 points you have observed. If you write out the autocovariance functions like this, you will get an expression that you can solve, and you will get the weights like this. And what you will see is that y of 3 hat, given the observations of y of 2 and y of 1, will only depend on y1 and y of 2, which makes perfect sense given this was an MA process, so you should be able to predict it using a combination of the earlier measurements. Let's proceed to examine an ARMA process. By dividing the A polynomial down, I can express the future value y of t plus k as c divided by e of t plus k. If I form this polynomial division, that will result in an infinite sum of polynomial coefficients like this. Notice that the first elements of this sum are future noise realizations, things that I definitely will not be able to have access to, whereas the rest of the sum will contain earlier noise realizations that I should be able to predict. Therefore, I rewrite the sum as one part consisting of the future noise values, those that I will not be able to access, as well as the earlier ones, which I should be able to access. I express the first sum as a polynomial using the fz polynomial. Since the f polynomial is a division by the monic polynomials a and c, the f polynomial will also be monic, so it will also start with 1, and will border k minus 1 since the sum goes up to k minus 1 like this. To simplify my notation, I do a variable substitution subtracting k, so I get a sum from 0 to infinity like this. I then note that this sum I can form by using the polynomial division by the c and the a polynomial. Basically, I will express my c divided by a as the part I can divide, that is the f polynomial, as well as the remainder, the part that I cannot divide, which I call g. Finally, to get both on e of t, I'll subtract out z to the minus k like this. I can compute the f and the g polynomials by solving this Diophantine equation, where the orders of the f polynomials will be found like k minus 1 as we concluded before, and the order of the g polynomial will be the maximum of p minus 1 and q minus k. Note that g of z will not in general be monic because it will consist of the kth element in the polynomial division, so there's no reason for this to be 1. As you know from the earlier discussion, we'll form the optimal linear prediction using the conditional expectation. Now I'm conditioning on the parameters of my model, which I assume to be known, as well as the earlier observations. That means that the conditional expectation of the future is formed by 2 parts, the first being the future noise realizations that I clearly don't have, as well as the earlier noise realizations. The expected value of the first part will be the expected value of the future noise realization. Since these are zero mean, the best possible way of estimating those will be to say that they're going to be 0, so this is going to be 0. For the second part, I note that e of t plus k can be expressed as a divided by c times y. Inserting this, I can see that I can cancel my a polynomial and I will just have g divided by, say, y of t. Note that this expectation is conditioned on theta here, which contains all my previous observations. That means that these are all known and the expectation thus goes away, so my predicted future will just be g divided by c of y of t. This will only depend on the earlier realizations that I have observed. The part that I cannot predict, the prediction error, I can write as the true future values minus the prediction. That will be the true future value which contains the f polynomial subtracted off the prediction which does not contain it, and of course then I will just have the f part remaining. The prediction error therefore will have the form of an mak minus 1 process. I can express the variance of the prediction error like this, which of course will depend on k, so it obviously is harder to predict the future further ahead. I can use that, for instance, to form the prediction interval to tell me how well can I expect to be able to predict the future at some point ahead. That means that if I observe a process like like this, and this is point t, I can form the prediction like this, and at the same time compute the confidence intervals of this prediction, and that will of course grow then the further ahead I'm looking. One conclusion from this is that when you see a prediction of the summer weather in the early spring, it's obviously not going to be very accurate. As I said, it is easy to predict the future saying it's going to be 20 degrees during the summer. I mean, obviously it will be at some point, probably, but the plus minus 20 degrees doesn't help you all that much, right? Let's look at an example. This is the 5-step prediction of a SARIMA process formed like this. The first thing I do is I rewrite the seasonal operator into an ARMA. That means that my A polynomial will be of this form, and I can tell then that P should be 13. My C polynomial, on the other hand, I can read off from here, and that tells me that Q is 12. This tells me that for a 5-step prediction, my F polynomial should be order 4, and my G polynomial should be order 12. If I perform the polynomial division, this is what I will get. That means that my future prediction will have this form. Notice in particular here that if I move this part over here, I will have one term looking like this. This term will be the prediction of the y of t plus 5 minus 12 given observation up to t minus 12. That's the same thing as y of t minus 7 given observations as y minus t minus 12. But notice that I have observations all the way up to t. That means that I know this sample, so I can just replace this by y of t minus 7 like this, yielding my final prediction like this. In MATLAB, I can form the polynomial division efficiently by using the function polydiv that we have provided for you to do this. This would be the example code to do the polynomial division for this example. Here's an example of 4-step prediction of a SARIMA process. For this process, if I multiply the A component together, I can see that the order P here is 26 and the Q is going to be 14. Since it's a 4-step prediction, that means that the order of the F polynomial will be 3 and the G polynomial will be 25. Doing the polynomial division using the polydiv functions, these are the polynomials I get. In order to visualize my prediction, I plot the t plus 4 prediction together with the true t plus 4 value, and as you can see, those are following each other pretty close. However, that's not the same thing as saying that this is going to be an accurate model. Can I do it better than this? To be able to tell that, I will look at the ACF and see whether I have further structure in my prediction error that I should be able to exploit. And looking at the ACF, I can see that the ACF indicates that this model should be well modeled as an MA3. That means that I have a prediction error of the structure that would be the one I can expect for an optimal predictor. It therefore is reasonable to assume that I cannot improve it further. Here's a further example. This is the temperature in Svedala, and this is the model I should be told to be using for that. And if I form a 1-step prediction, this is what the 1-step prediction of my data looks like as compared to the true measurements. This seems to be fairly white, although I do have some components outside, but if I do whiteness test, this will deem to be a white sequence. It would also tell me that my ACS is reasonably well Gaussian distributed, so meaning that I can trust my tests accurately. So this seems to be a white noise, and I should be happy with that as a 1-step prediction. To stress my model further, therefore, I try to make a 5-step prediction. Of course, I will need to compute new G and F polynomials for that. And if I plot the prediction, I will get this form. That doesn't look as nice as before, but is it good enough or is it not? The question is hard to answer by just looking at the prediction. But if I look at the prediction error here, this does not look like an MA4, suggesting that perhaps one can improve the model further. However, this is not certain. It might also be that the season or the model is changing over time, so meaning that my model structure or my model coefficient cannot be expected to be stationary throughout the time. Then this is typically going to happen too in my prediction. I'm not able to predict the weather 4 steps ahead using such a simplistic model, or doesn't have time-varying parameters, so I am not able to do such a prediction, and that is actually quite common. For almost all models, you will have this problem at some point or another. The model is just simply not sufficiently good to predict that far ahead into the future without being further refined or allowing for time-varying structures, taking into account such things as the seasons are changing, or that your assumptions are just simply not valid that far ahead in time. For this example, this is not the case. So if I go back to our identification procedure, I look at the model and I'll conclude that some of these coefficients that were just slightly outside, maybe I should have included those into my model. I will find my model and get a new A and C polynomial. I will recompute my F and G polynomials, and I'll do a new prediction. Looking at the prediction, that doesn't look all that much better. However, looking at the ACF, I can see that now this has a clear MA structure and all my higher lags are gone. Interestingly, note that this is not an MA4, but rather an MA3. The theory just dictates that my prediction error cannot be improved better than an MA4 in general. Here, it happens to be that the 4th coefficient is smaller than my confidence interval, so therefore I can actually express it as MA3. That is just being lucky, giving me a lower prediction variance. Returning to the mortality data in the UK that we built a model for earlier, I now use this model to do a 1-step prediction on my validation data. That is data that I haven't seen before, and trying to see whether my model is a good fit to this data. This is the 1-step prediction compared to the true mortality, and as you can see, I'm following the curve quite closely. And if I look at the ACF of the prediction error, this can be deemed to be a white sequence, and the prediction error and the ACF for this one, they are also normal distributed, telling me that this is a reasonably good model, and I can therefore trust my 1-step prediction to be accurate. If I use this model then to do predictions ahead of time to see what should have happened if there hadn't been a pandemic, I can tell that this is the deaths that I should be expecting to see in the UK if there had been no change. Given the F polynomial, I can compute the confidence interval, and as you see, this is clearly growing as time goes into the future. It is harder to predict the future further ahead. But you can also see that the number of actually observed deaths clearly are significantly higher than the ones we expect to see. If I compute the difference between the actually observed number of deaths and the one that's predicted by the model, we can tell that the pandemic has caused about 15,000 additional deaths at this point. Quite interestingly is that when we did this modeling in the early spring, the UK media reported about 4,000 additional deaths. That was the number of deaths reported by the hospitals. But as you can see here, the additional number of fatalities clearly was much higher than that, just because of the reporting of deaths from hospital as being pandemic related didn't capture all the deaths that were occurring due to it. So a better measurement of the number of surplus deaths would be the difference between the expected mortality rate and the observed mortality rate. That will tell you how many additional people actually died from the pandemic.